The U.S. Navy has quietly been building a new kind of fleet, autonomous submarines that can chart the seafloor, patrol for months without surfacing, and make choices in total darkness. But during one test that seemed routine, one of those drones simply disappeared. For hours there was nothing, no signal, no sound, no light. When recovery crews finally hauled it back on deck, the video stored inside revealed a story no one expected. Beneath the waves, a quiet shift is underway. The United States Navy is assembling a fleet of machines that don't need air, rest, or a human crew. They can think on their own, glide for months at a time, and reach places no manned submarine could safely go. These are the Navy's underwater drones, part of a fast-growing web of robotic subs moving from test tanks into open ocean. At the center of this new generation is Orca, a huge, uncrewed underwater vehicle built by Boeing and derived from an earlier prototype called Echo Voyager. Orca is massive, roughly the length of a city bus when fully assembled, stretching about 85 feet from bow to stern. Its signature feature is its midsection, a 34-foot modular bay that can haul roughly 8 tons of payload. That compartment isn't fixed. It works like a removable cargo trunk, letting shore crews slide in different mission modules depending on the job. The Navy's initial plan for Orca is to quietly plant naval mines in selected areas of the seafloor. But that's only the starting point. The same internal bay can be packed with deep ocean mapping sensors, advanced surveillance equipment, and more. Getting there, however, has been anything but simple. The Government Accountability Office reported that costs rose by more than 60% above the original estimate, and the schedule slipped by at least 3 years. What began as a plan to deliver 5 working vehicles quickly became a struggle with the realities of building a first-of-its-kind submarine. Even so, deliveries have started, and Orca is now moving from Boeing shipyards into Navy testing. For the Navy, those delays are worth enduring because Orca offers something priceless: endurance. Its hybrid propulsion lets it cruise silently on batteries, then recharge with a diesel generator when it nears the surface. That mix of stealth and staying power allows it to remain on station for months, traveling thousands of miles without a support ship. In practice, it becomes an unseen presence that can patrol coasts or gather intelligence far from home without risking a single sailor. While Orca is all about size and stamina, another design takes a different path. Manta Ray, developed by Northrop Grumman for DARPA, the Pentagon's advanced research agency, focuses on efficiency. Where Orca is big and muscular, Manta Ray is sleek and economical, engineered to move like the creature that inspired its name. It recently finished full-scale trials off Southern California, showing it can operate for long stretches while using little energy. Manta Ray glides through the water by shifting its buoyancy, rising and sinking like a living animal instead of forcing itself forward with heavy propulsion. When needed, small propellers give it short bursts of speed. When they are not, the craft can rest on the seafloor, slipping into a kind of hibernation to conserve power until the next mission phase. During testing, it was shipped in modular pieces, assembled on the beach, and sent straight into the surf. That field assembly approach means it doesn't burn fuel just getting to the worksite. It starts its mission exactly where it's needed. DARPA has already confirmed that parts of this design are being reviewed for Navy adoption, a sign that Manta Ray is more than a science project. It's a template for how the Navy can field underwater drones that last not just hours, but months. A third vehicle completes this trio, Yellowmore, a torpedo-sized drone that can be launched straight from a submarine. Unlike Orca or Manta Ray, which depend on surface support, Yellowmore is built to fit inside a standard torpedo tube, allowing submarines to deploy and recover it without special equipment or divers. In the spring of 2025, the fast-attack submarine USS Delaware reached a historic milestone when it fired a Yellowmore from one of its tubes, sent it on multiple long missions, and successfully recovered it each time while deployed overseas. The Navy later confirmed that this trial happened not in home waters but in Europe during an active patrol. That single event, described as the first forward-deployed submarine torpedo tube launch and recovery, proved that these compact drones can become everyday tools for submariners. A crew can dispatch a robotic scout ahead through a narrow strait, scan a harbor, or inspect the seafloor without exposing their own vessel. Together, Orca, Manta Ray, and Yellowmore offer the clearest glimpse yet of the Navy's underwater future. Much of this work takes place around Naval Base Ventura County in California, using the Point Mugu Sea Range off the Channel Islands. During major exercises, locals often see more Navy ships offshore, showing how busy these waters are. As unmanned programs grow, the work comes with real risks. In early summer 2025, a trial near Ventura showed how unpredictable these systems can be. During one test, a towed unmanned surface craft unexpectedly switched into autonomous mode and capsized a small support boat. Fortunately, no one was killed, but the Navy immediately shut down operations and investigated before resuming. Testing is difficult because of how these machines survive underwater. Communication, navigation, and recovery all work differently beneath the waves than they do on land. In the ocean, radio signals die quickly. Wi-Fi, radar, even basic voice radio can't travel through seawater. Instead, drones talk using sound, slow, low-frequency acoustic signals that reach only a few miles. Links might hold for half a mile to 3 miles, carrying just a few thousand bits of data per second, enough for commands, not live video. So most drones store everything on internal drives and send back short updates until they surface. Once an antenna breaks above the waves, they can switch to satellite or radio for faster data transfers. Navigation is just as challenging. GPS signals don't penetrate below the surface, so each drone has to track its own motion with an inertial navigation system, a bundle of gyroscopes and accelerometers that measure direction and speed. No system is perfect though. Tiny errors build up over time, so the vehicle's estimated position can drift by roughly a nautical mile every hour unless corrected. To stay on course, drones periodically surface for a GPS fix, listen for underwater beacons, or use sonar devices called Doppler velocity logs to measure their speed relative to the seafloor. When it's time to come home, each drone relies on an acoustic pinger, a simple underwater beacon that emits a distinct tone. Recovery teams on nearby ships use hydrophones to follow that sound, triangulating the location until they find the vehicle. Many pingers are designed to trigger automatically if the main power fails, so crews can still follow the signal. Those three pillars, sound for communication, internal sensors for navigation, and pingers for recovery, are what make underwater autonomy possible. Now that we understand what these machines are and where the Navy tests them, we have to ask what happens when one suddenly vanishes. Often, it begins quietly. An underwater drone just stops answering. It follows its route, sends short acoustic data bursts, and then the ocean goes silent. In deep water, silence is normal, but when it lasts too long, it becomes alarming. A lost signal can mean a dead battery, a crashed computer, a snag on old fishing gear, or a glider pushed off course by the wrong current. Engineers plan for all of that, yet when contact is fully lost, a routine mission turns into a high-stakes search. To see how fast that silence becomes serious, it helps to look at real incidents that force the world to pay attention. In December 2016, a U.S. Navy vessel called USNS Bowditch was running a routine ocean survey in the South China Sea. On board was a small underwater glider, a slow, unarmed drone built to study seawater conditions. Unlike torpedo-style vehicles that push with propellers, gliders move by changing their buoyancy. They gently rise and sink using short wings to turn that motion into a forward glide. It is a quiet, efficient way to measure temperature, currents, and salinity, used by researchers and navies worldwide. That day, the Bowditch crew was preparing to recover their glider. It surfaced on schedule about 50 nautical miles northwest of Subic Bay in the Philippines and began transmitting a homing signal. Before the crew could reach it, however, a Chinese naval ship closed in and, without warning, hoisted the drone out of the water. The Bowditch crew watched as their equipment was taken away. Washington called the act an unlawful seizure and demanded the drone's return. China kept it briefly, then handed it back a few days later. That is one way an underwater vehicle disappears. The other kind of disappearance happens when the ocean itself closes in. In early 2024, a 7-meter autonomous underwater vehicle named RAN vanished under Antarctic ice. RAN belonged to a University of Gothenburg team led by Professor Anna Wallin and operated from the South Korean icebreaker Ara-an, which was studying how warm currents erode glaciers from beneath. RAN had already made important dives in the same area, mapping an extremely remote region. On the last dive of this expedition, it simply did not return. It never appeared at its rendezvous point and never answered locator pings. Search teams swept the area with acoustic receivers and helicopters, listening for any trace of a signal. Nothing came back. After days of effort, the crew had to accept what everyone feared. The batteries had probably died, and the robot was gone. Under Antarctic ice, this kind of loss is not unusual. The ceiling overhead is solid, so the vehicle cannot surface for GPS. It has to rely entirely on dead reckoning and sound. Dead reckoning means estimating position by tracking how far and in what direction you have moved since the last known fix. Every sonar ping drains power, and strong under-ice currents can shove the vehicle off course. If it misses its pre-cut hole or drifts beneath rough, ridged ice, it can become trapped. Designers add fail-safes, backup beacons, strict time limits, and emergency abort routines. But once the power is gone, the silence is permanent. Not every disappearance, however, ends in a loss. Off Southern California, a very different scene unfolded. During a test at about 90 feet of depth, a Navy-class Remus 600, a 600-meter rated autonomous vehicle used by militaries and research groups worldwide, became snagged in an old line on the seafloor. A nearby commercial diving and robotics team spotted the problem and moved in to help. They launched a small remotely operated vehicle, or ROV, fitted with a camera, grabber, and hydraulic cutter. Watching live video, the ROV pilot followed the tether down to the stuck drone, found the line, cut it, and brought the robot and debris back to the surface. Together, these three events, the South China Sea seizure, the Antarctic loss, and the California rescue, show a larger pattern. Underwater drones do not simply vanish into mystery. They are bound by physics, hardware limits, and probability. When one goes missing, crews fall back on a strict, well-rehearsed playbook to bring it home. The first step is listening. Most underwater drones carry a pinger, a small acoustic beacon that helps teams track them by sound when they go silent. Once the pinger is heard clearly, the ship traces search patterns, tightening circles or figure-8 loops to narrow in on the source. It is slow, methodical work, but it shrinks the search area dramatically. If the mission was planned with extra care, the team may have placed a few acoustic transponders on the seafloor ahead of time. The vehicle talks to these beacons, and by timing how long the sound takes to travel back and forth, operators can triangulate its position. This approach is called long baseline tracking because the beacons are spread far apart, hundreds or even thousands of feet, to boost accuracy. When there is no chance to seed the seafloor with beacons, a ship can rely on its own sensors and a faster system called ultra-short baseline, or USBL. A cluster of receivers under the hull listens for the pinger and estimates direction and range. In deep water, it is less precise, but much quicker to deploy, and in emergencies, speed matters more than perfection. Once sound has guided the crew close enough, the next phase is seeing. Search teams lower a towed side-scan sonar, a long metal fish that sends out fan-shaped pulses. As those pulses bounce off the seabed, the sonar builds an image of what lies below. Objects appear as bright streaks with dark shadows behind them. An experienced sonar operator can recognize the outline of a vehicle, a net, or an anchor line in those patterns. Using side-scan sonar, searchers sweep the area in parallel tracks like mowing a lawn underwater until the missing drone's shape appears. Once they have that image, they mark the coordinates and move to the final step, touching. A tethered ROV with lights, cameras, and manipulator arms descends to the bottom. Its pilot watches in real time, steering with joysticks and nudging the robot toward the target. Power and data run through the tether, so the ROV can stay down as long as needed. If the missing drone is tangled, the cutter can free it. If it is upright and intact, the ROV can grab a handle or attach a sling so the crew can hoist it to the surface. This toolkit, pinger, sonar, and ROV, is how most lost underwater drones are recovered. In ice-covered or cluttered waters, the methods are adapted. In polar operations, for example, teams sometimes mount a homing receiver on the ROV so it can follow the drone's beacon through narrow tunnels beneath the ice. Once the vehicle is back on deck, the job is not finished. What it recorded is often as valuable as the machine. Its data drives, whether memory cards or solid-state storage, are treated like forensic evidence. Each one is labeled, sealed, and logged before anyone opens a file. Analysts then pull the data under strict national procedures to preserve timestamps, sensor readings, and metadata. That discipline ensures the record of what the vehicle saw can be trusted. Over time, those recovered logs have revealed scenes on the seafloor far more disturbing than anyone expected. Haunting images from the seafloor. In April 2023, a team from Scripps Institution of Oceanography sent high-definition cameras down along sections of the old dump corridors in the San Pedro Channel. The dive was meant to be a simple follow-up check after a mapping survey. Instead, the cameras revealed rows of shapes that looked far too organized to be random. When the researchers zoomed in, the gray sonar blobs resolved into metal cylinders and steel containers. These weren't lost tools or scrap barrels. They were World War II-era munitions. Some were anti-submarine depth charges, heavy steel shells once packed with explosives. Others were smoke floats, small devices ships tossed overboard to lay drifting clouds of concealment. The wreckage lay in long, curved trails across the bottom, as if a ship had calmly rolled them off its deck at a steady pace. Follow one debris trail long enough, and sooner or later another weapon appeared. The Navy's public response did not dispute what the cameras found. Officials said many of these weapons were probably dumped in the 1940s, back when using the deep ocean as a garbage pit was standard practice. Warships returning from patrol simply jettisoned unused ordnance on the way home. But that brief camera run was only a glimpse of something much larger. 2 years earlier, in 2021, the same stretch of seafloor had been mapped in detail by autonomous underwater vehicles towing side-scan sonar across roughly 36,000 acres, around 56 square miles. Those robots detected more than 27,000 barrel-shaped targets with high confidence, plus well over 100,000 other bits of debris. Picture a city-sized plain where every few yards another drum or crate lies half buried in mud. That is what the sonar outlined, and it explained why later camera dives kept encountering dangerous relics. The munitions alone were unsettling, but the video revealed something stranger. Around many of the barrels, the seafloor looked as if it had been dusted with chalk. Each drum sat in a pale ring, a white halo glowing faintly in the lights. At first, researchers assumed glare or disturbed sediment. But the rings appeared over and over. The halos were real. For years, scientists suspected a link to DDT, the banned pesticide known to persist in Southern California's marine food web. DDT contamination in nearby seafloor mud and animal tissue was already documented, but no one had directly tied those ghostly rings to what was inside the barrels. In 2025, Scripps researchers went back with new sampling tools. They paired barrels that displayed halos with others that did not, then collected sediment cores from right beside them. The lab results were shocking. The pH, the scale that measures acidity and alkalinity, was about 12 near halo-marked barrels. That value sits at the extreme alkaline end, the opposite of acidic, and it means the mud is caustic enough to burn skin like bleach left too long on your hands. In that kind of environment, almost no microscopic life survives. The sediment turns sterile. Chemical tests explained why. Leaks from the barrels were reacting with magnesium in seawater to form brucite, a mineral also known as magnesium hydroxide. As that crust slowly dissolved, it released more alkaline material, driving the surrounding mud back toward that same extreme pH and leaving extra white deposits of calcium carbonate behind. The halos were not stains. They were active chemical scars marking where highly caustic waste had seeped into the seabed. That finding pushed the story far beyond DDT. The pesticide is still a serious problem in this region, but those halos show that many barrels were filled with something entirely different: potent chemical waste from refineries and factories. This kind of dumping doesn't just poison fish and marine mammals. It rewrites the chemistry of the ocean floor itself. It can turn metals like zinc or aluminum into more mobile forms that move with currents and build up in living tissue. Those white rings are the first visible fingerprints of that hidden process. To understand where this is happening, imagine a deep section of the San Pedro Channel called Dump Site 2. It sits roughly midway between the Palos Verdes Peninsula and Santa Catalina Island, about 12 miles from the mainland and 8 miles seaward of the already contaminated Palos Verdes Shelf. Dump Site 2 is only one of more than a dozen deep-water dumping areas scattered along the Southern California Bight, the broad sweep of coast running from north of the Channel Islands down toward the Mexican border. Some sites received industrial sludge. Others took surplus military gear and explosives. Records trace these practices back to the 1930s and show them continuing in various forms until the early 1970s, when international rules finally shut down this kind of ocean dumping. The cameras also revealed another truth about this coastline: the seafloor does not separate old from new. In one frame, a World War II canister lies buried in silt. In the next, a snarl of modern fishing line or electrical cable cuts across the view. Decades of industrial activity, fishing, and shipping have layered generation after generation of debris on top of one another. And California is not alone. Around the world, clearer cameras and longer-lasting underwater robots are uncovering forgotten chapters of human history. In early 2025, a French Navy training dive in the Mediterranean accidentally found a 16th-century merchant ship more than 1.5 miles down, over 2,500 meters below the surface. The wreck held stacks of ceramic jugs and iron bars, preserved by the cold, high-pressure water. Seeing what lies down there is one thing. Deciding what to do about it is another. So what comes next for the Navy? After the 2023 survey, officials said they were reviewing the findings and trying to choose the safest path forward, one that manages the risks to people and the environment. Leave hazardous material on the bottom and it continues to leak. Try to move it and you might trigger something worse. Either way, someone has to decide which option is less dangerous, touching it or leaving it alone. When old munitions or toxic barrels turn up underwater, the Navy and its partners treat the problem as two separate hazards. One is the blast risk. What happens if a bomb is disturbed? The other is the environmental risk. What happens as the object corrodes and leaks into the sea? In deep water, far from boats and swimmers, the odds of a random detonation are tiny. That means in most cases, the safer choice is to leave the object where it is and keep watching it. In shallower water, especially if a weapon looks unstable, they make the opposite call: plan a controlled detonation or lift it out. The Defense Department even funds dedicated research programs just to study those trade-offs. They are called SERDP and ESTCP, and their purpose is to test exactly when a buried weapon can stay under observation, when it is safer to blow it in place, and when it is too risky not to remove it.
Every location is different. Depth matters, currents matter, the makeup of the seafloor matters. And now, off Southern California, chemistry matters too. Some barrels on the bottom have leaked so much alkaline material that the surrounding mud burns like bleach. It is toxic even to microbes. If someone disturbs those white halo zones the wrong way, that high pH material could spread into cleaner areas. That is why every decision now has to rest on data, not gut instinct. The Navy is not facing this alone. The Environmental Protection Agency and the National Oceanic and Atmospheric Administration are working alongside it on the Catalina Dump Corridor. Together, they are building a shared map of what lies down there and which regions pose the greatest risk to people and sea life. Los Angeles County has been kept in the loop, and the EPA maintains a public website tracking every update on Dump Site 2. That kind of partnership means any Navy decision has to fit into a broader plan, one with paperwork, clear responsibilities, and outside oversight. It also means smaller steps can move forward right away. Agencies can tighten no-go zones, deploy more sensors, and keep surveying while long-term cleanup choices take shape. Zoom out one more time. The drones that filmed all of this are not one-off gadgets. They are part of a growing fleet the Navy expects to use year after year. Congress has already built that into the budget. Beginning in fiscal year 2026, the Navy is scheduled to receive one new extra-large underwater vehicle each year through fiscal 2029. Thanks for watching. Now check out the videos popping up on your screen for more unbelievable stories from the depths.